is to progress on to the next lecture in this sort of whirlwind tour through these basics of any logic. I'd like to now go and open up this lecture 8. It's the lecture on state charts. Okay. So the idea here is we're going to represent here discrete agent dynamics, meaning we're going to represent agent behavior as transitioning among a set of mutually exclusive, collectively exhaustive states within a state chart. Okay, so they're going to evolve between a set of states in this construct called the state chart. And for a given simple state chart that we'll be looking at here, an agent's in exactly one state at a time. In general, we could have nested state charts, hierarchical state charts, which are described by my online material on YouTube if you want to check them out. Fixed transitions between states defined fixed transitions. What I mean by that is transition is present or not between two states in a persistent way. They define the persistent evolution. And the transitions between states occur instantaneously and based on some conditions. So ladies and gentlemen, I'd like you to take the model that you already have open, or alternatively, I've provided a model of the heterogeneous agents, which if you're having trouble with your model, you could actually load it in the model from the O drive called heterogeneous agents. But if yours is working, I'd encourage you to save that. And I'd like you to do save as, file save as, and call it simple state charts, okay? Simple state charts. This is just going to be a very, very basic glimpse of state chart functionality. So we're calling it simple state charts, okay? So we've saved the model. In practice, it's a very good thing to save away successive versions of a model, so you can go back to those versions at any point. You can recreate earlier findings and not simply overwrite your models, okay? Okay, I'd like you to double click on person to open up the canvas for person in case you don't already have it open. And I'd like you to add a state chart entry point, okay? How do we add a state chart entry point? Well, you may have to scroll down depending on what you see visible. In the palette, there's an area called state chart, and I'd like you to drag that up there. And I'd like you to just leave it as state chart. Okay, there's a kind of weird thing said here, but that's fine. Just leave it, it's called state chart, okay? And then we're going to add some states to this person, okay? In the interest of sticking with script, I could have made these work and home for Edgar's question earlier, but I'm going to instead hew to my script to avoid confusing people. I'm going to drag up from state charts a first state. So if we drag it up here, I'm going to call this state susceptible, okay? So where do we do that? We dragged up from state, and we dragged it so that it aligned with the bottom here, okay? You'll notice if you click on this entry point, you should see a green dot where it intersects with the state. That's an indication that it's corrected. Who needs help here? Who needs help? Yeah, Dylan, maybe you could catch Kate up here. Who needs help? Okay. So what did we do? We opened up, Dylan, we opened up person, and then we dragged in a state chart entry point called state. It's just the one we've been working on. So if that was working, she should save it. However, do save as and call it simple state charts. Okay. So we dragged in a state chart entry point. We dragged in a state called susceptible. We named it susceptible. Okay. And one thing that's a good practice to check is this a real connection? If it's green, if you click on this entry point and you see a green connection, that's a sign you're good to go. Okay. And then I'd like to add a new state. And I'd like to call it infected, okay? And so we added a new state, dragged it over, we called it infected, and then I'd like to add a transition between these states here called infection, okay? How did I do this? I'm going kind of fast here. I dragged the second state into here, and then I dragged the transition between them. You'll notice both these sides are green. I was lucky in that regard. If those two had been further apart, you might have gotten something like this. When you dragged it in, I'll sort of illustrate it. You might have gotten something like this, where, you know, I could connect it on one side, but on both, I'd have to drag it up there, okay? But the point is that that transition should be called infection. Okay, who needs help here? Who would like help from a TA? Who would like double checking from a TA? Okay. Okay, so what I'd like to do here is, okay, there's a kind of a strange thing here. We're going to leave that as a default. There's a disjuncture from the slides here. So I'm going to do a print screen of this to sort of replace this one. Okay. All right. Okay. Sorry, folks. I'm just correcting a slide. Okay. So we need to beware of loose connections here. Basically, if it's green on both sides of it, you're good to go. Okay, I'd like to add a recovery transition as well. So we're going to have an infection transition, and then we're going to have a recovery transition. For the moment, we're going to assume natural recovery is possible. And this, you'll notice that these transitions are defined as a very particular orientation to go from someplace to someplace. So I'm adding a transition and calling it recovery, and I'm not changing any of their characteristics, okay? You'll notice that each of these transitions has a semantics associated with them. It says timeout, timeout 1, timeout, timeout 1. So I'm just leaving that for now, okay? I'd like you now, ladies and gentlemen, to go run this model, okay? I'd like you to run the model and see what you see. So who needs TA help? Okay, so what do people see here? So let's drill down to the level of an agent. What do people see? So ladies and gentlemen, you tell me, how do I drill down to the level of an agent? How do I run the model, first of all? Okay, okay, good. If people laugh, it's a good sign, then they're comfortable with that. Okay, how do I drill down to an agent? Sorry? Okay, drop down, good. Okay, so what do I see here, ladies and gentlemen? At the level of the agent, what's going on? What action is taking place? Okay, they're changing states. They're going from one state to the other, back and forth. Okay? Okay, ladies and gentlemen, what I'd like to do now is to go and we're going to take that visualization, we're going to take that and visualize it more nicely. And I apologize, folks, but I'm going to stretch you a little bit here some more. So we're going to want this agent to change the color of the circle around them. Okay? So their circle, we're going to have its edge change color based on the infection state that they're in. Okay? So, anyone want to, first of all, who's responsible for setting the color of the edge of the circle? Where would I go to look at that color? So person, it's in person, because we're dealing with the property of a person. And it's in dynamic of what? Is it dynamic of a parameter or dynamic of a state chart? Of the circle. Because it's a property of the circle. It's a characteristic of the circle. True or not? True. Thank you, Wendy. So let's click on the circle. And if we scroll down, we'll find, in fact, there is a thing for line color, line style, and line width. Let's make the line width, let's say 10, okay. Excuse me, line width 5. Excuse me, line width 5. But what are we going to say for line color, folks? I tell you, my slides say one thing, but I'm going to do something else, which I think is cleaner. And I'll let my TAs give me feedback and once they see both versions. Okay, folks, what am I going to say for color? The line color around them. How could I tell it to be a different color based on their infection status? Where did we set their color before? How did we? Anyone tell me? How did we set the sort of overall circle color? Does anyone remember that? Yeah, there was a Java phrase, or what we call in Java an expression. An expression is something that computes a value. It's a formula that when we use it, it computes a value, it gives us a value, as opposed to a statement, which is a command. Do this. This is an expression. It computes a value. I like the phrase sort of reference. This computes a value. So that's how we set the formula before. So maybe we could do something here for line color. But folks, how are we going to tell? I mean, so we want this line color. We could have it be like either black or white, or we could have it be either red or blue, based on something. But what is it going to need to depend on? I'm trying to get you to think like how to go about this, how to decompose it. So for color, what do I need to put there? What does it plausibly have to depend on, ladies and gentlemen? On the sorry? Oh. If I have the vocabulary right, okay, I can define it, but let's suppose I wanted to change. It's a good point. I can do it based on recovery rate. But let's suppose I wanted to change color based on what state I'm in. How if I want to change from, say, green when I'm in a susceptible state to yellow when I'm in an infected state, or something like that? Okay. Yes. Almost. So essentially, it's an if, but it's an if expression type of thing. It's something which evaluates if this thing is true, return this value, otherwise give that value. It's very comparable to this. So in other words, this is like an if. If this thing is true, then it's pink, otherwise it's blue, right? So we want something very similar here. And you said it exactly right. It was something about if I'm in the susceptible state or infected state. And so now, ladies and gentlemen, I'm going to contaminate you further with Java. So here we are going to have to ask, are we susceptible? How do we ask that? Well, ladies and gentlemen, when we ask, for example, are we susceptible? We might have several state charts, one for HIV, one for TB, one for Hep C, and each of them might be susceptible to that or infected with that. And so we have to ask the state chart. We have to say, hey, state chart, a particular state chart, the HIV state chart, or the TB state chart, or the Hep C state chart. In this case, there's only one state chart, but we have to ask it, hey, am I susceptible? So how do I ask it? I say state chart, and this dot means sort of, hey, I'm addressing you. I'm addressing you, state chart, and I say, is state active? Now look at that. What did I just do here? This is your friend, folks. folks, welcome into your life a valuable, well, a very kind and generous friend. So statechart.is, and you do control space, and this thing will pop up. So is state active? So this is basically asking the state chart, okay, hey, state chart, is some state active? Which state? And I'll say susceptible. Is that state active? If so, I'm going to be green. Otherwise, I'll be red. Okay? What is this question mark thing? Where did we see the question mark before? Thank you, Dylan. Control space is auto with a big hard around it. Yes, thank you. Thank you. Well put, Dylan. So what is this? Can anyone read to me what this is? What is this question mark and colon? Where did we see that before? The blue and pink. We saw it before. It means if this thing is true, then green, otherwise red, right? Right? So, and this is saying, hey, state chart, is my susceptible state the active one for you? Remember, right now it may seem weird we have to address the state chart, but in general there can be many state charts. I have a TB state chart, I have a diabetes state chart, I have a hep C state chart, I have an HIV state chart, and we want to ask, we need to ask for each, a particular state chart to be a meaningful question. So here we say, hey, is my state active? If so, I'm green, otherwise I'm red. Okay? Okay, who needs help here? So this dot is basically saying, it's sort of like I'm asking state charts. You can think of it as almost like I don't have the right word for it. It's like a apostrophe. It's like Nate's is state active, or state charts is state active. I'm asking it if it's susceptible, because that's who's responsible for telling me, okay, whether it's susceptible. That's who's responsible for maintaining this information. I say, hey, is this state active? So I'm green, otherwise I'm red. Okay, who needs help with that? I'm departing from script here a little bit, but I think this is actually cleaner. Okay, so ladies and gentlemen, if we run this, what should we see? Can anyone tell me? Okay, so let's run it. So what's going on here? So why is it? First of all, why are these things changing? Because the underlying agent is changing state. This agent is changing state. Right now it is susceptible, infected, susceptible, infected, susceptible, infected. Oh, why is it? Why are all the blinking in the same sort of hideous unity? This, right. Now I want to highlight this, because if we went down and we drilled down to a particular agent, we might not have recognized that they're all going at exactly the same pace. It was only by doing this high-level visualization we actually realized, oh, they're all actually synchronized here. These visualizations, ladies and gentlemen, I want to stress the fact that after years of command line programming and so on, these visualizations are not merely eye candy. Visualizations can sometimes give you the big ahas in what is going on. They can help you recognize patterns you would never have seen otherwise through all the statistics you could have put out. Okay, but let's go and ask, why are they all blinking in unison? Why are they all blinking in unison? Can anyone tell me? Okay, so why do they change at exactly the same moment? This is what I'm trying to drill down to. What is it about our specification? We specified the state chart. What is it about our specification that led them, ladies and gentlemen, to transition at all the same moment? There's a lack of stochastic, and why is there a lack of stochastics? Oh, Okay, so we talked earlier about this rate transition. By contrast, what transition do we have here? We have a timeout. And that means there's no stochasticity. It's exactly after one time unit, in this case a day, after they come in here, that they come in successful, they leave here. And then exactly one day, it's the same thing for this guy, though I'm not showing it right now. Exactly one day after. So ladies and gentlemen, let's now let's preserve the overall timing in terms of averages, but let's introduce some stochasticity. Let's have their transition to the affected process be described by a rate, by this first order delay process. In other words, by this Poisson arrival with a lambda of 1. In other words, a hazard of 1. And let's run this. What do we expect to see differently? Now this is with a rate of 1. Still the mean time, ladies and gentlemen, with a rate of 1, a hazard of 1, what's the average amount of time they spend in the susceptible state before getting infected? It's 1. It's 1 over 1, which, so it's the same amount on average, but will it look different? Ladies and gentlemen, will it look different? Okay, so why is it looking different? By the way, we can speed these things up. You could make it blink, at all different rates. You could make it here. So what's going on here, ladies and gentlemen? It is now, why is it desynchronized? Because there is stochastics. Now we have stochastics. We have stochastics of when they get infected, even though when they get recovered is exactly one time unit after infection. Okay? So we've just seen, yes, 1. 1. So that was the hazard. A rate of 1. I was preserving the timing, Dylan. Just making the point that even with the same timing, the qualitative behavior is rather different. Okay? The same average time. That's an average. If it's a rate of x, the average time in the state would be 1 over x. For going to that, if that transition alone were considered. So, and yet now we have this sort of very different behavior. Okay. Okay. So there we go. We have the simple state chart here. Okay. Suffice it to say, I don't have much time to talk about this, but many types of transitions are possible in any logic. Any logic supports transition types listed here. Timeout we've seen, spending exactly some period of time in the state, no stochastics. A fixed rate, this is a hazard. This is a first order interarrival time. It's a memoryless Poisson arrival process. There's we could have a variable rate where the rate changes actually over time. So you can actually have time changing hazards, but there's a little bit of finesse required with that just to make sure it updates accordingly. You can transition when a message is received, when a condition is true, such as there's no more infection in the population or whatever, or when you reach a location as you're traveling. Okay, so when you reach a certain destination, you can go. And transitions can also be conditionally routed via branches, as we'll see. So we already examined this. Okay. Let's just so I mentioned hazards, right? I think just to sort of upstage, right? So. We've already seen self-transitions. It turns out any logic distinguishes self-transitions drawn external to a state versus those drawn internally, which is interesting. So you've got to be clear. Those external actually leave the state and come back in. The ones internal to a state do not. Took me a bit of time to appreciate that, actually. And these branches can be used to put people in different states. There's also special types of states, such as death state, which are sync states. In other words, you go to them and then you don't leave them. and those might be associated with deactivation of agents or agent disappearance. We can have multiple state charts for different conditions, which can be more or less independent, although with some interactions where desired, which allows for very nice decoupling if you have comorbidities. For example, if you have Hep C and HIV and TB considerations all in one patient, you can capture their successive natural history of infection with respect to each in a fairly decoupled fashion, which is quite nice compared to what you can have with compartmental modeling. I think and we can inquire as to how long someone has been in a given state quite easily. I would note that there are, and I have more elaborations on this online, one can readily have composite states which are hierarchical in nature, and these can be very, very handy. For example, if all internal states are subject to the same death transition, you can just have a death transition from the outer state, and it will make sure that you could transition from any inner state according to the same conditions. You'll see a glimpse of that later in the week. I provide some comments here, including this is state active. I think given the amount of time we have, I'm just going to do one more thing here in preparation for a later lecture. And specifically, what I'd like to do here is to address a question that came up earlier. What if we would like to have individuals within this model start out actually in different states? This will be less critical here, but it'll get more interesting in an infection transmission context. Okay, so where we want some people to start infected, for example, to kick off the transmission of infection in the population. So let's suppose we wanted people to come into the state chart, but some start susceptible and some start already infected. How would we do that? How would we do that? Okay. Yes, there is. So we could actually have some fraction that start infected. And let's suppose here I want to have. I could do it with extra parameters and so on, but given that I want to do this in about 5 minutes, I'm going to just cut it short. Suppose we want 5% of the population to start in the infected state here. I'll show you one way to do it. So I talked earlier about all these different things that can be done with state charts. We can have all these, hierarchical things, branches, and we can have these final states, etc. Which of them will be relevant? I'm trying to get you folks to be able to sort of go from question to answer here. If I wanted people to come in and be divided initially between susceptible and infected, how could I do that? Which of these constructs would allow me to kind of divide up people initially? So some people enter here initially and some people enter here. A branch. See this branch here? So, ladies and gentlemen, let us actually go do that. So let's take this state chart here, and let us go drag a branch in here. Okay, and you'll notice that it is connected. So we could drag a branch in, and then we'll have one transition from the branch which will go to susceptible, and then we'll have another transition from the branch. Oh, and that guy got hitched up there, but I want him down actually to infected, okay? Now that looks ugly as sin right now, but we'll fix this up handily in just a moment. So what did I do here, ladies and gentlemen? I moved the state chart up off the top, and I dragged in a branch, and then I dragged a transition in to go from the branch to here, and another transition in to go from the branch to the affected state. Okay, so the problem is that these two things are sitting almost atop each other, so I'm going to have to kind of finesse this. Okay, so I'm clicking on the one under there. I want that one to be the default. Okay, so in other words, by default, someone starts susceptible. Eh, Yeah. Okay, yeah, who needs help here? TA stand ready. TA stand ready. Ready for deployment. Okay, okay. So this other transition out, Dylan will want to note, is we're going to do a condition on it. And this condition will be, under what conditions will we go to infected? Well, under the condition that something is true. And we're going to use a thing in Java called random true, excuse me, a thing in any logic called random true. And we give it a probability of being true. And it will flip the dice. It will flip this weighted dice. 5% probability to be true. 5% probability to be true. The 5% probability will go this way, otherwise it goes that way. Otherwise it goes the default way. Okay? If we do that, we should be able to. Okay, now it's okay. Yeah. This is okay. We now have these two things there. Okay. Yes. And it's, pardon me, it's saying too many default exits. Okay, this is the normal runaround I have with this. Pardon me, I'm just gonna detach it there and attach it back on here. Okay, and there we go. Okay, that's a strange thing. Scott should take note of that. But basically, I had to detach it and reattach it, and now it works fine. Yes, indeed. So here what we have is we have two transitions, and I'm gonna, to route this better, I'm gonna double click on this one and route it around here, okay? And that will make it look quite a bit nicer. And I'm gonna in fact double click here and route it around again, so that it comes down in a more sort of graceful arc. Now we have, again, two transitions. One out that says, so this is start, I'll call it start susceptible. And this other one that says start infected. And that will allow some part of the population to start susceptible, some part to start infected initially. In this case, it's not too obvious, but some ended up going down this way and some ended up going that way. How could we, ladies and gentlemen, how if I needed, I want you to think about, I want you to think as a debugger, this will be the last thing before lunch here, we're about to break, but how if I wanted to test, is this thing working? Are some people really starting susceptible, some people starting infected? How could I test that? How could I test that? Well, there are several ways. One way would be to just disable any movement between these states. So I could use a rate of 0 between these states, for example. So no one can move that way, and no one can move this other way, for example. So I'll set a rate of 0 going between the states, and I'll run it, and then I'll see if some people start infected and some people start susceptible. And indeed, that's exactly what happens. Okay? So that'll be one way to test. Here, all I did is I disabled this transition and disabled that transition. But I did it in sort of a crude way. I'll show you another way in any logic to do it that's a little bit more slick. I'll change this back. So any logic has this ignore feature in it, which allows you to basically say, pretend that's not there. And I could run that, and okay, so this thing is element is not reachable. Okay, so that's interesting. Oh, okay. It doesn't allow me to do the ignore. Okay, well, so much for a beautiful idea killed by an ugly fact. Okay. So turning off the transitions by setting it to a rate of 0 is a reasonable idea. Another way, ladies and gentlemen, will be to get us to tell us that it's actually gone down this path. So specifically, I could go over here, and you'll notice that each transition has an action associated with it. And we're going to have our model for the first time talk back to us. And that's a good thing. So we're going to click on this transition, and we're going to type down in the action, trace ln, I am starting susceptible, exclamation point, and then semicolon. So can people see that? This is trace ln, begin parentheses, quote, I am starting susceptible, exclamation point, and then end quote, end paren, and semicolon. Okay, TAs deploy. And then I'm going to put a similar statement in for this transition here. I am starting infected. Okay? Here the model will actually talk back to us. It'll actually tell us who's starting susceptible, who's starting infected. Okay? And we're going to run this now. And what we'll see is that there's a bunch that report. Some people say they start infected. Some people say they start susceptible. Okay? So I just look at this console. Yeah. So folks, I just looked in this console here, and it can report back to us right here. Okay. Who needs help here? Who needs help? Are people comfortable with that? People okay with that? All I did is I inserted in these two places something called a call to trace ln, which basically gives it a message to print out. Print out here one message, print out here another message, and then we went to console, and it's printing out information here. Okay? And so some of them are starting susceptible, some are starting infected. Okay? So ladies and gentlemen, you've seen some of the basics of state charts, seen some issues of how do we get the population to do it in the initial state, one way to do that. Now it's time for lunch. There was originally a lecture scheduled for today, but because it'll be given by a colleague in Singapore, she's requested it be held at another time during the week, later in the week, on Thursday or Friday, early in the day. So we're trying to accommodate that. So I'll give my vocal cords a rest, and we'll go over to the faculty club, have a meal, and rejoin here in about an hour's time. Okay, so you can stay logged in here. Okay, but one thing you could do, it's a great question, you can do file, save as here, and on your computers, you should be able to do it to the H drive. Pardon me, I'll just this one here.
You also have USB drives. You could save it to that. You put the
Yeah.
USB drive in, and you can save it.
Yeah. So you can either save it to your H drive, or you could save it to a USB drive that's provided to you. And one of the TAs would be glad to help you with that. Yeah. Yes, yeah, we'll make sure someone stays here to walk our story. Thank you. Actually, what I'll do is I'll lock it up. Okay? Yeah. Unless someone wants to stay like in the room instead, I'll lock it up. Okay, so we'll go over to the faculty club and reassemble here in about an hour's time.